Hello everyone, I am Suchita Morit from St. Vincent Pallotti College of Engineering and Technology, Nagpur. In this video, we are going to discuss higher order differential equation with constant coefficient part 1. Main objectives of this video: students are able to understand the concept and knowledge of higher order differential equation, and students are able to apply appropriate case for solving examples of higher order differential equation. Types of ordinary differential equation: first order differential equation and higher order differential equation. Order and degree of differential equation. Order of the differential equation is the higher derivative appearing in the differential equation. For example, here in this equation, highest derivative term is d2y by dx square. Therefore, order of this equation is 2. Then degree of the differential equation is the power of the highest derivative term. Now power of this highest derivative term is 2, therefore degree of this example is 2. In this way we find out the degree and order of the second equation. Now here highest derivative term is dy by dx, therefore order of second example is 1. Now power is also 1, therefore derivative degree of this equation is 1. Now we consider nth degree nth order term equation. That means here highest derivative term is nth term and right hand side is function of x. Now first we write down this equation in symbolic form by substituting d by dx equal to capital D. This is the symbolic form, and this complete bracket first term we consider write down as f of d term, this y as it is phi of x. Now solution of this equation is given by y equal to cf plus pi, where cf is complementary function and pi means particular integral. Now cases for finding cf. Here first we substitute, write down the equation in symbolic form by substituting d by dx equal to d. Then d equal to m in f of d of y equal to 0. This we call this as auxiliary equation, and then we solve this auxiliary equation, find out the roots of the equation, and last step is according to the nature of the roots we write down cf. Now case 1, we apply this case for whenever the roots are real and different. Whenever the roots are real and equal, we apply case 2. Whenever the roots are imaginary in the form of alpha plus minus I beta, then we apply case 3. These three cases, for these three cases we consider second order differential equation. That means there are two roots. Now for fourth case we consider four roots. That means two pairs of imaginary roots are equal in the form of alpha plus minus I beta, then we apply this case. Now we consider here pi first case. Now first we write down pi in the form of this 1 upon function of d into phi of x. Now pi cases is depend upon this phi of x term. Now case 1, whenever there is right hand side is, that means pi of x is e to the power ax. Now 1 upon function of d into e to the power ax term. Then we substitute d equal to a. D equal to a, that means here function this d is replaced by a term. A means this value. Then here 1 upon f of a into e to the power ax, provided the value of this f of a is not equal to 0. If this value equal to 0, that means case fail. Then we apply another method. Multiply the term by x and differentiate the f of d term with respect to d. E to the power x write down as it is, and again substitute d equal to a. The condition is that again this this value f dash of a is not equal to 0. If this value equal to 0, again apply same method, find out the values. Now we consider here one example which is based on case of pi1. Now here right hand side of this equation is e to the power minus 2x, which is the higher order differential equation. Therefore solution is given by y equal to cf plus pi. Now first we find out cf. We write down the auxiliary equation. Auxiliary equation d is replaced by m plus 2 m minus 1 whole square and right hand side equal to 0. We solve this equation. The roots are these: minus 2 1 1. Minus 2 is real and different, therefore we apply case 1 here of cf, and then here 1 1 means repeated value, repeated roots, therefore we apply case 2 of cf. Here c1 plus x c2 e to the power x term, and here minus 2, therefore we write down here minus 2 term, which is the required cf. Now for pi, this is the method with 1 upon d plus 2 into d minus 1 whole square, here e to the power minus 2x. We substitute d equal to minus 2 because here value is a value is minus 2. Then if we substitute minus 2 here, minus 2 and plus 2, its value equal to 0, that means case failed. Then we multiply the numerator by x, differentiate the denominator term with respect to d. Now derivative of this term, here we derivative of this first term value is 1, then this value as it is, derivative of this term is this d plus 2 as it is, then again substitute d equal to minus 2, then we get x by 9 e to the power minus 2x, which is the required pi. Lastly we write down complete solution y equal to cf plus pi, that means a plus b. This part is cf, a equation, this part is pi, that means b equation, and which gives the required solution. Now case 2. Case 2 is for right hand side is sin x or cos x. For this we substitute d square equal to minus of a square. Now here minus of a square, provided this f of minus of a square is not equal to 0. If this value equal to 0, again apply same method, that means multiply numerator by x, differentiate the denominator term with respect to d, and again substitute d square equal to minus of a square, and provided this value is again not equal to 0. If this value equal to 0, again multiply by x, that means x square, then 1 upon differentiate the terms again, that means 1 upon f double dash of d square into sin ax plus b value. We consider another example which is based on case 2. Here right hand side of this equation is sin x, which is higher order differential equation, therefore solution of this higher order differential equation is given by y equal to cf plus pi. Now for cf we first write down auxiliary equation by substituting d equal to m in this equation here. Then right hand side of this equation is 0. We solve this equation. These are two roots. These two roots are real and different, therefore we apply case 1 here, cf case 1, and write down the required cf. Now pi of this equation, 1 upon f of d into phi of x. Here substitute the values of f of d and phi of x term. Now here substitute d square equal to minus 1, therefore we get this value. Now here we taking phi u common from this equation, then we get 1 upon phi u into d plus 1 sin x. Now our substitution is for only for d square, not for d, therefore we multiply and divide by d minus 1 and forming d square in the denominator, therefore we get this value. Now apply here formula d plus a plus b, a minus b, that means a square minus b square, therefore we get this value. Then substitute d square equal to minus 1, we get this term. Now when this d in the numerator, we differentiate it. When this d in the denominator, we integrate it. Therefore this d in the numerator, therefore derivative of sin x is cos x, and minus sin x as it is denominator term is minus 10, which is the required pi. Lastly, we write down the complete solution y equal to cf plus pi. Here this first part is a equation, that means cf. Second part, this part is b equation, that means pi, which is the required solution. In this way we can solve the problems of case 1 and case 2 by applying this same method. Thank you.